don't live in this state. So
if anybody else knows of any, kid-friendly coding groups,
Go to codinggame.com.
codinggame.com.
Yep.
Sweet, thank you.
Coding Game, Code Wars, those are designed for people in elementary to high school
Okay.
to learn how
thank
to
you.
code.
Actually, I'm not
just start now.
Yeah, that's fine.
one that just felt like it set up. I'm not sure if the Forum Library is still doing it, but they have a young technologist, and I think once we,
Young technologists.
yeah,
Okay. That's a local group there.
at Forum Library.
Well, library. Okay.
I'm not sure if they still do it or not.
All right. So
Good check.
thanks for telling me those that are here.
Thank you.
We're going to talk about RHOLANG, which is our current programming language that we're going to be using in the RHOLANG blockchain, as about how you can play around with it today and what works as of now. Okay, so some background. RHOLANG is an implementation of the row calculus, just like you might call Haskell or ML an implementation of the lambda calculus. And it's got additional features to make it better for end-user programming. So the row calculus, so the row is actually an acronym. It stands for reflective higher order pi calculus. Those are kinds of mathematical models of parallel programming that have been around for a long time. And so one of the insights that led to row calculus was that most of the pi calculus presentations just assume there's some set of names. And in row calculus, Greg Meredith, who created the row calculus paper, he wanted to add structure to names. And so he realized he could just reuse the structure of processes to get a structure on names. And as we go along, you'll see why this is significant. So in order to get anything done in RHOLANG, all computation really happens because of either a send or a receive. So sends go to a single destination. We call the destination of a send a name. You can think of it as like the name on an envelope, or the name gives you an address where you can meet with people that are expecting the data you're sending. You can actually use names as a key value store, and maybe I can show you that. So that's send, and then for every send, unless you're just like, the golden record on Voyager, you need a receiver. So receive in RHOLANG can have multiple sources. So there's this asymmetry. Sends are singular, receives many, at least one. And this allows you to do things like take atomic clocks. And you can do it, or to only fire a piece of code when data is available from two different sources. And here's a quick example of what some sends and receives look like. So here we have a send to a channel named standard out. And in fact, if you write the quoted string standard out in the existing RHOLANG interpreter, it will actually print things out, have an effect. And then this doesn't work yet, but you can fake it by adding a send to standard inline. But this line, if standard inline were a special channel with something listening on it, this would read in a line from standard in and write that line to standard out. All right. So like I said, all of the computation in RHOLANG occurs because of sends and receives, and they're on. Sends and receives require names either to send on or to listen on. And they need to know, the names need to be the same in order for something to happen. So in RHOLANG, all names are quoted processes. And the way you write quote is you use the @ character. And you've already seen this used on the previous slide. So standard out is a process, @ standard out is the name, so the quotes around it. The string is the process. So quoting it gives us the name, and we can produce a send on the process quoted string standard. So
Core developer.
yeah, he's one of our interns.
Start with name then, huh?
All right. So names are quoted processes. So given a name, we might want to actually use the process that's quoted as a process. So we can use the star to reference it. And if you look, I was sneaky and I stuck that into the example. So X here is bound to a name. And then over there, we use X as a process to send the value on send. All right. We're going to cover sends in a little bit more detail, and we'll go through receives, and then there's some other things in RHOLANG besides send and receive. But until you understand send and receives, none of the other stuff matters. So you got to do send and receives first. So a send takes a name, and that name is this part right here, and a list of processes. That's this list right here. So if we go back to this slide, that's a quoted string, so it's a list of size 1. And I believe that sending lists of size 0 actually works at the moment, but I'd have to go check. So here's a send. We're going to quote this process, 7 plus 8, and we're going to send the values 9 and 10 plus 11. And then, one at top level, you'll see what I mean by top level in a minute. But top level expressions, in general, don't get evaluated. But here, when we quote this expression, we do actually evaluate what's inside, and the time when it's evaluated is on the actual send. We leave it alone until the send actually turns out we're actually going to evaluate the send right now. So first we need to evaluate any top-level expressions in the quoted process. And we also evaluate any expressions, any top-level expressions in the quoted processes that we're sending. So if you evaluate these two things in parallel, so here's a send on 7 plus 8, and we're sending the value 9 and 10 plus 11. And if we were to listen on channel 15 for the evening news, and so we get these two values and we send them bundled as a list to standard out. And this is the actual output. I checked it while I was working on these slides this afternoon. So it actually prints out the list 9 and 21. This is just an artifact of, it should just print the list 9 and 21. So that's some more detail about sends receives. Similarly, if there were an expression in the channel you were listening on, so like this is listening on 15. If this were listening on 9 plus 6, this would also work because we would reduce this channel when we would evaluate the expressions inside of there before we tried to do the actual listening. All right. So receives can be from more than one channel. So here we have one send or one receive listening on 2 channels, A, quoted string A and quoted string B. And here we have a send on A of 74 in parallel with a send on B of 75. And so executing this will print 74, 75. Great song, nobody knows it. All right, so the receives are a little bit more complicated than sends, so there's more information. Oh yeah, that's because of patterns. So in general, it's been looking like, well, we can get a variable, from a receive, and we send a single thing. And here we can get multiple variables. And the number of things that you send has to match. But in fact, it's a lot more, it's a lot more powerful than that. We'll expand on how powerful it is as we go through. The simplest kind of pattern flip back is just arity matching. So this send sends 2 values, and this receive is expecting 2 values. And if this receive were expecting 3 values, or this send only sent 1, they would not match. So both things would be running in parallel, but neither would trigger the other. So what happens is when there's a send and a matching receive, the send disappears and the body of the receive executes. And if they don't match, they both just stick around waiting for a send or a receive, respectively, if it does. So we can talk more about what the patterns are and why they're powerful. So the patterns are structural types for names, and the way that you produce a structural type for a name is to quote structural type for a process. Kind of works out nicely. There's symmetry between the type of a name and the type of a process. It comes from you quote a process to get a name, and you quote a type of a process to get the type of the name. If we have time and interest, I can go over what you can do with matching, but we may only just scratch the surface. And I'm going to sneak in some syntax that I haven't shown you yet, but this is an example from, or a snippet from one of the examples that we ship with the distribution. So this, we can read most of this, except for this bit right here already. So this is a pattern, so here's a pattern. There are 2 patterns. This read right here is expecting exactly the process, the quoted string get. Exactly that. So no, anything else in that first position will fail to match. And it's expecting an arbitrary name, ret. So ret is a free variable, and even if it were bound, it's considered free here because this is a good shadow. So this matches anything, and this matches exactly one name. Okay. And we're reading from method, and you can assume that method is bound somewhere outside. And then over there, so we've quoted the structural type val. So val is the type, or val is a binder, but it also matches an arbitrary process. But the nice thing is that inside the body, ret is treated as a name, and val, because we put the at in front of it and quoted a process pattern, is treated as a process. So and maybe later I can pull up the context where this came from. But basically, we have some channel state. We're going to read the value from state whenever we get, whenever someone sends on the method channel the string get and a return channel, and we're going to write whatever was on the state channel to that return channel, and we're also going to put the state back because we like to clean up that ourselves. So down here, so that's one thing you can do. You can simulate method calls, and you can specify. This actually kind of acts like a lock. It sequences read. If someone were trying to modify the state, they would have to take the value, modify it, and then put it back. So this is an explicit synchronization between readers and writers. Here's another example. So this, we can quote a list here. Why wouldn't you just use array matching? There's reasons. One example, one reason you might is that you can use these same patterns in our spatial matcher. And we'll get to that in a minute. But this right here would bind X and Y, provided that whatever was sent on A was a list beginning with 7. So if we were to send 7, 8, 9, and then we were to print it out, can anybody guess? So if we were to execute, these are separate segments. If we were to execute just this segment, can anybody tell me what would be printed on standard out? 8, 9. Yeah, it's the list 8, 9. So that's what would get captured.
Why is the first index not included in?
Well, no, it is. It had to match, but it's not a variable.
Oh, it's only printing the variables without.
Yeah, it's printing X,
Yeah.
comma Y. If we were to print 7, X, Y, then it would print 7, 8. Yeah, exactly. So it's staying over there. All right. So one of the other things that you can do is you can do a remainder pattern. So you can say, I want this method to fire if I get n or more items. So like a good example of this would be, this feels a lot like printf in C, where it's required to pass a string and then a variable number of arguments after. So you can specify a remainder pattern. So unlike the other patterns in the slot, you can't specify a more complicated remainder pattern. Because if you knew what the remainder was going to look like, you could have pulled that off and made that part of the pattern. So you're not really losing, if you know what the remainder looks like, you're not really losing any functionality by us saying, no, your remainder you can only just quote of R. You can also do ... at underscore, which is a wildcard, and we'll just throw away the remainder. So underscore is like a variable that doesn't bind. There's some subtleties in the matcher, but I can get that in there. And for now, underscore just acts like the variable, but it doesn't act like a binder. So then variable is bound to a list, which is those square brackets that we saw earlier. The list could possibly be empty, and it's whatever's set above the things already supplied. So if we execute this example where we send on a yes, no, I don't know, and we can say for remainder X from A, print out the X, and then you'll see that it's been turned into a list. Yes, no, I don't know. So if we were to put at quote yes, comma, and then this, we would print no, comma, I don't know. All right. Like I mentioned, each receive has the body. When we decide that the patterns in the receive match data in the send, the data in the send is considered consumed and it goes away from where we're tracking what's available. And then any binders in the pattern are made available within the body. So it's kind of, you think of it like a function call or a let statement.
So is this just the language that RHOLANG is written in?
No, this is the language that we're implementing so that we can write, that will be running on the RHOLANG blockchain.
Okay, so can you say that one more time? Sorry, I didn't get that.
So RHOLANG is, we're working on programmable blockchain like Ethereum, but instead of Solidity, we'll be deploying things in this language called RHOLANG.
Oh, cool. So are you gonna talk about our chain or just the?
I'm just talking about RHOLANG today.
Oh, okay. I must have misread the meeting. Is there gonna be anybody talking about our chain here? Or just?
I can answer your questions today.
Oh, okay, cool. I'm just gonna take a potty break. I'll come back. Thank you.
All right. So there's a couple things that we need to talk about when we have sends and receives together. One of them is you can have competing sends and receives. Maybe we should talk about this pipe here. I realize I didn't do that. So this pipe means these things are running in parallel. So we have a send on A running in parallel with a send on A, running in parallel with a receive. Oh, that should be. There we go. Flat out. So along with one receive on the channel. So if we were to execute this, it will either print 18 or 19. And unfortunately, I think it will just one of them. It shouldn't, but it does. And a similar, we call this a race. A similar thing would happen if there were one send and two receives. Or you can get a K by L race where you have K writes and L reads.
What is this based on?
This is based on there are a bunch of what they call process calculi that are models for parallel processing. And they use these kind of communication models. And this one's based off of a particular one called, like I said, one called row calculus, with some things that make it easier to use. The row calculus is very much a model and not intended for like, oh, I was going to go write something. All right, so there's some send and receive asymmetry. So if you're paying close attention, you might have noticed that we were sending processes and receiving names. So that's an intentional asymmetry. And the goal was we figured people would use names of processes about equally. And we didn't want to privilege one over the other in terms of like sending it and receiving it. And so it's actually, it seems weird, why would you do that? But like once you kind of get used to reading it, it kind of feels nice that like, oh, well, when I receive, I know exactly what I'm getting. And when, it balances out. It actually feels nice. Most of the time, if you, right, like if you're sending on a name, you'll see a star. And if you're receiving a process, you'll see an at in pattern. And there's kind of a balance. I kind of like the balance. I think it's aesthetically pleasing. But semantically, we could have done it, like you always send and receive names. And so like it's not like it's just an aesthetic choice. It doesn't really change the way RHOLANG works. It just changes the way that RHOLANG looks on the page. All right, so it's a nice overview of send and receive. And so now we're going to talk about some of the other things that RHOLANG does in addition to send and receive. It'll make it, because send and receive are the engines of computation, and they're like actually what makes stuff happen, it makes sense to talk about them first and then move on to the other. So, hold on, I realized I just completely skipped out on expression, but that's fine. So, enrolling, everything is a process. You'll notice that we quoted the string A. So this send 7 is a process, but so are the string A and the number 7. If you were to just try and evaluate them, they don't do anything. So I actually have an interpreter here, and I'll blow this up so that it's moderately legible. So like, you can run 7, it's a process, but it doesn't do anything. And similarly, nil is the empty process. The string A is a process. So that, at the moment, you can't, other than, I'll show you in just a minute. There wouldn't be any problem adding that to the language, it's just not something that we did. All right, so if they're behaviorally equivalent to the empty process. So if we take an arbitrary process P that's running at the top level, and we put it in parallel with the string A, it's going to behave like it's not going to change P. It's going to be true for any P. There's the processes for which that is true for all P. They're called ground processes. So we have the atomic ones with booleans, strings, ints, and URIs. We plan on adding byte arrays to handle cryptography. So you produce some bit of code and turn it into a byte array and then verify a signature. So all of the crypto functions that we're planning on working on will work on byte arrays. Byte arrays are ground terms. And so we have lists, and we're working on sets, maps, and tuples. There's not completely fleshed out. But for an arbitrary process X, the list containing X is a ground term, even if X is gone. So, but it's not an atomic ground process. It just, if you take something and make a list out of it, and then you put it in parallel with P, it's not going to have any effect. Being in a list kind of negates its effect. And so expressions, almost all of the expressions will only, if they successfully evaluate, will only evaluate to ground terms. So like addition, or string concatenation. So we don't evaluate them at the top level because we know if they succeed at evaluating, they're going to produce a term which has no effect. So we just don't bother reducing them at all, because we know that and in fact, there are a few expressions that are in the source that are for instance, method calls can produce. So like we have on list, we have a method called nth. So like this list.nth 0 would extract x, and now that process if x is not a ground term can have side effects. So there are a few things that we do actually evaluate at the top level. Okay, so moving on. One of the things that RHOLANG has that's definitely not in row calculus, well, it could have been, new. So new gives you unforgeable names. And what that means is that when this evaluates, this produces, like you can substitute, so it substitutes in a value for x, which you couldn't write in the syntax. And so if we were to run this snippet, right here, new X and X bang unforgeable for message from X, standard out. Nothing really surprising here, right? We were using the quoted string A to do a lot of this same thing earlier. But now, if you remember, I'm not going to flip all the way back, but remember that we could have races on the quoted string A. Well, we know where X is, we know that X didn't escape and didn't get sent anywhere. So there are no races possible on X. So this is always going to print unforgeable, no matter what context it's running in, because we know that nothing else can create a name that got assigned to X and race so that something else gets there. It turns out that this is an incredibly useful property for security. It allows you to do, and I kind of wish Mike were here, but this allows you to follow object capability discipline and use object capability style security. And that's the kind of security that we plan on using in the RHOLANG blockchain. All right, so matching. I mentioned before that the same kind of patterns that are available as receive patterns are available for the match instruction. All right, so we can go through this. So contract, oh, I remember, I didn't explain the, contract just creates a replicated read on one channel. So contract loop means listen on loop, and it gets pattern. So we're listening for a list, and we're going to match that list with the, so that's a variable. We're going to match it with head, and we're going to bind the remainder. So remainder syntax is available for lists as well. And then we're going to print to standard out the head, and we're going to call loop with the tail. So we're going to invoke this contract again, so it's just an actual loop. And we're going to call the loop on 1, 2, 3. Now, anyone care to guess what's going to get printed? Ooh.
Hello world.
Just kidding. No. So, sorry. So, what's interesting is the print to standard out is in parallel with the reinvocation of the loop. So it's going to print out the numbers 1, 2, 3, but the order in which they get printed is not guaranteed. And in fact, the current implementation prints them 3, 2, 1 every time.
Just because there's a race.
Yeah, it's because it's a literal race. They're racing to see what gets read by standard out. So yeah, at the moment it produces 3, 2, 1. It should actually produce an arbitrary permutation with a preference to, with one being more common at the beginning because of timing.
So if you had a list of 50 numbers, instead of just 3, then it would be random every time, probably, or?
No, what you would expect if it were actually being non-deterministic is that the time that it took to evaluate the loop would cause the early numbers to be likely to be read by standard out.
Right, because the loop has to reread the small list. So
Yeah.
it will take just a little longer ways to get the numbers.
Yeah, so yeah, like what happens is that, yeah, it's a literal race, but each number in this, each number at the head gets a longer and longer head start. So if it were actually being non-deterministic, you'd expect that one would occur at the beginning more often that it's non-deterministic. All right, so what if we wanted them to print in order? All right, so it turns out we can actually make them print in order. And the way that we do that is we use, so this is a common pattern, you'll see this a lot. We're going to use the return channel, and then we're going to wait until the return channel, until something is actually printed and before we call the loop again. So this looks basically the same, except we allocated two names, loop and ret. And then we're going to send standard out ACK, the head of the list, and the ret name. And then we're going to list it on the ret name. And it turns out this is already implemented. There's a standard out ACK. So what it does is it prints the first value, and then after it is done printing, it sends a message on the ret. Well, that's the light time of day when they. It's going to turn it off at 8 o'clock. So here we listen for an arbitrary message from ret. We don't use a binary because we don't care what it is. And then we just loop on the tail. And so this will print 1, 2, 3 every time. And it's guaranteed by the semantics, even if we were actually being non-deterministic instead of like just being predictable. It would always print 1, 2.
What is the T1 exactly? So the HD, which is the head.
Oh, sorry, that's TL.
TL?
Yeah,
It's like,
HD and TL.
So it takes the first member of the list and tails the list.
Yeah. So, all right, that's the end of the presentation. I'll go ahead and stop this. Although, maybe I'll start again to answer some questions. All right, so let's, where are we on time? Yeah, it's about 8 o'clock. Does anybody have any questions about RHOLANG?
so the bang is the send character, right?
Yeah.
And then the at symbol is the
Quote.
Are there different types?
At the moment, no, so you can send on an arbitrary, there are two types, they are processes and names. And you can convert between it, you turn any name into a process, like quoting, you can turn, I think I probably talked about dereference. Yeah, and then you can turn any name back into a process by using the star. We plan on adding additional typing to cover some other things.
Like what?
So we want to be able to specify what kinds of things you expect on a channel, so that you aren't just expecting arbitrary. You aren't having to deal with arbitrary things coming in. You can specify. It will allow you to have better compile time guarantees that your code will execute as expected. You'd say, like, I'm only expecting to read integers on this channel.
So this would be like the same syntax as the actual smart contracts.
Yeah, this is what smart contracts will be written.
Yep.
There's some other things that we'll add, but the goal of this presentation, so like this is the RHOLANG interpreter.
I see it.
Oh, fantastic.
Is there like, what's the word I'm looking for? Is there somewhere where we can see what each symbol means? Like just a breakdown of the syntax. Like the bang is send, the at is the name, and RET is a channel. Like, is there some place that just has all those defined?
There's a tutorial to take you through it.
Okay.
Yeah.
So, is this a newer language?
Yeah, this is brand new. It didn't exist until I made it.
I see. Specifically written for RHOLANG.
Yeah.
Yes.
Could we go over the structural types of names and like just a few examples of different structural types of names?
Sure. So
What signals does the smart contract run?
So what causes it to run is that like, you deploy, you put some code that that matches a send that was already deployed or a receive that was already deployed.
So it's just like a key that gets sent and they match. It's like, okay, go.
Yeah.
Okay.
Yeah, it's like a polar, so it's a polarized key value.
So what are the benefits to using this language as opposed to the existing?
So some of the benefits are that because the parallelism is ingrained and the data dependencies are explicit on keys, it allows you to take the parts which it allows you to do a very simple proof. The two things don't interact. They don't share names. They don't interact. So that allows you to parallelize it really well.
So if this is based off row, like selected higher order calculus, what is the process? Let's see if I'm saying it right. The process type that Ethereum would use.
Ethereum runs on the Ethereum VM, but it uses Solidity, which is an actor model. It doesn't really fit into this kind of model.
Are there other ones that use different models besides like row and?
I don't know. So I can tell you what happened was I got interested in the blockchain, I don't know, 2014 or 15, and I realized it wasn't going to scale. And so I was like, yeah, whatever. Like, write me when you guys invent something that's going to scale. And so I stopped being interested. So, but like, what piqued my interest was, I knew the guys running this company, and they like actually planned something that would scale from the beginning. So that's why I'm in Utah. Among other reasons, I like it better.
So that parallelism or whatever you call it, is that a scaling feature or a security feature?
Oh, okay. The parallelism is a performance feature, very much so.
I see. So that's what gives you the ability to confirm blocks quicker?
It's more about being able to. So one of the problems in Ethereum right now is that everything, because you can't prove whether two things do or don't interact, everything has to be sequentialized. And so that gives you no ability to like shard things effectively, or makes it very difficult to split problems that could be split. And here we know, you know by inspection whether two things can move. And so this allows you to do things like, oh, well, you deployed code A and I deployed code B, and we don't have to fork, we can merge because our code doesn't interact. And that proof is short, right? Like, you just take the set of names and you do it that we interacted on. And do
Whereas, sorry, so like if Ethereum did that, there's a chance of where they do interact and then it executes, and it's bad.
So you can't, in Ethereum, you have to pick one fork and rerun the other thing. You can't do a merge like that.
Right.
Those computer languages are inherently sequential. So if it happens, then the next thing, then the next thing, then the next thing, and you have to go to great lengths to make things
A check
happen.
that runs to make sure they don't match, and then if it doesn't,
This language
if there's no
is
match, then
designed
merge.
so that everything is inherently parallel.
And in fact, you could do a
And
partial
so-
merge where you say, oh, well,
Instead of having like
I'm going to
one-
use my
almost like
fork choice
regular
fork.
languages, one person
you
just doing
you
everything.
included these 15 user
And
transactions,
RHOLANG,
and I
you
can
can have
tell
a
that these
bunch of
14 don't conflict with
little
what I've got
pieces
here,
of
so I can pull them
programming
in.
that are
So
more
just
like.
rerun the other one, or how does
Yeah,
that
and
work?
then you would be responsible
But they
for
can talk to each other.
rerunning these other ones.
But just
You do this, you do that, you
that makes things a
do
lot
testing,
easier.
you do testing, you do testing, when you're done, send a message to him. to do
What are
testing.
you
So on.
using to code this? I don't know.
So it's all
This is
inherently
based on
parallel.
like C or like.
So
It
the
makes-
software
it makes
automating is
the-
installed.
Makes
Okay.
the processing inside the computer much
We
more
use that
efficient. Because if
At
you
the start of that, I
now
worked
say,
at
okay,
for data
I
analytics.
can start these three running and then
It's
when we finish, I can start this one.
They kept telling me it was like really similar to Haskell, more immutable or something.
So from a
They
security
said-
standpoint,
Scala is less immutable than Haskell.
as secure,
Yeah.
more secure than.
I was just watching them just, I don't know, data science just, it's amazing me.
That's been a question for
You can
Kyle.
tell their speed from like X,
Not sure I
point A
can-
to point
I'm
B,
not
and
sure I
somehow
can.
they figure out what you have to practice.
Hey Kyle,
Yeah,
so gentleman here has a question about whether this makes the R chain more secure than Bitcoin, Ethereum, and so on.
the parallelism property, no, it just makes it scale better.
Okay. So,
But you can build in security if you want to.
Yeah,
and forgive me because I'm not a coder and a lot of this is just going over my head, but the issue as I understand it is that it's because transactions take so long to confirm. Is this like a side chain thing or is it just a completely revolutionary technology that's allowing you to do? I read somewhere that our chain can do up to 40,000 transactions per second.
so
How do you do
I don't
that?
know why people keep saying that. At the moment, our chain does 0 transactions per second. because It doesn't exist.
40,000 is the goal set.
That's our goal. That's the.
So, yeah,
It's our success
there's all kinds
criteria.
of stuff on the web. It's like, we've confirmed tests that, I'm like, really? I gotta see this.
Well, whoever's running that is fine. Because at the moment, our chain has done 0 transactions.
Okay,
per
okay.
second. Right,
So do you think it will be able to do anything close to that?
I do think that the technologies that we have will scale. I'm not going to make any promises yet. Other people have made promises and then told me to try and meet them.
When you say scale, are you talking transactions per second or?
Yes.
Okay. So what would cause somebody to even speculate like that? I mean, and is it just like?
I'm not going to say I'm being recorded.
Yeah.
I'm not going to make any additional claims, and I'm not going to confirm or deny any of the existing claims. I'm going to say that at the moment, our chain does 0 transactions per second because it's still being built.
I see.
It's just like a Ford being built can only go 0 miles per hour until it's all the way. It's like,
So is RHOLANG sort of the secret sauce to Arching?
it's one of the secrets.
Okay. Does it Arching have side chains?
You mean like where you can have your own coins or tokens?
No, I
Where you
know what you mean by
confirms-
side chain. No, our chain is a different architecture.
Oh, okay. I see.
When it launches, it's just going straight to.
Yeah, you're asking about just side chains, like,
Yeah.
yeah, you will have a whole bunch. That's kind of what Mike covered, if you watched the meetup from what Mike stated.
Okay.
So yeah, the 40,000 where that gets is, obviously that's a goal, like Kyle said.
And you know how people are, they'll
Yeah.
hear a goal and say all of a sudden, yeah, it does that.
It's a working prototype.
But yeah, that's what we want to do, because we don't want the limitations of like Ethereum.
Yeah. So, I mean, is the goal to replace fiat currency with this coin? Part of it.
Our goal is to get a working blockchain, if that scales.
What's the ETA
Yeah.
thing? It's December, right?
Yeah, so we want to have an actual blockchain launched by December.
How many nodes are you gonna start with?
Another in-person ads.
So you guys did an ICO, right?
No, we have not done an
Okay.
ICO.
So you just got VC money?
So there's a token called RHOLANG, but it's not an ICO.
Which is different from Arching.
Rock is an Ethereum ERC20 contract. And it will be redeemed for the, at some point for Rev, which will be the currency, the native currency for the Archie.
Isn't there something about pyros?
Yeah, but those are for art.
I see. So what I'm seeing on CoinMarketCap is it's just a token.
So it's a utility token. That means that if you don't know what it's for, you shouldn't buy it.
Yeah. Yeah, I haven't bought any of it. That's kind of why I came here. Just wanted to see what was going on.
The point of owning Rock would be because you wanted to have an initial stake of Rev in Archie.
Will it be a
So-
1-to-1 when it first launches?
Yeah, it'd be more than that.
It will be evenly distributed according to the people who currently own Rock. So in the end, does it matter if it's 20 to 1 or 1 to 1?
Sure. Is there a cap on the?
Yeah.
What would the cap on revs be?
I don't know what the cap on that is still in flux again.
So I'm just trying to figure out, like, because it hasn't really been built or tested, why should I believe that it is going to be this revolutionary thing?
So I have provided no evidence today that you should. That was not the goal of my talk.
Yeah.
So
Okay. So, I mean,
if you really thought my talk on RHOLANG was great, that might give you some confidence.
Yeah, you can look away. I mean, we try to have things transparent, so you can see, you can go in, it's open source, view the code, you know, I mean, that's kind of where it comes. We have like our, all this other stuff's posted on YouTube. So you do want, we like transparency because it's part of the program and stuff like that. So you can do that, but just like Kyle said, until things you like see it doing stuff. And so we do have releases, but obviously until it's like actually doing stuff.
right. Do you have a place where we can get updates on it?
Yeah, if you just go the www.rchain.coop is kind of the main site, and they are updating a bunch of them. There's probably easier developer.rchain.coop.
Pretty good.
And you can get, that's probably the best place for it to get kind of the development.
Where can I read the tutorial for RHOLANG?
So if I wanted to run it by my friend who's a developer, that would be the best place.
Yeah, I would have them go to developer.rchain.coop, and then I think you can subscribe for releases, and then that will link to our GitHub and stuff like that. So GitHub/rchain/rchain.